Hello again, Year 8, and welcome to Lesson 7 on acids and alkalis. So what will you need with you today? You'll need a pen, ideally blue or black, to fill in your booklet, and a pen in a different colour so you can make corrections or mark your work and we can see where this has been done. So for today's lesson objectives, you're going to describe what colours bromophenol blue indicators turns in acids and alkalis. You're going to investigate how bromophenol blue indicator can be used during neutralization reactions. And you're going to understand how neutralization can be used in everyday life. So to start with, you need to get your spider diagram back out, add another branch for lesson 6, and as usual add 3, or at least 3, different bits of information that you remember from last lesson. And if you can't remember 3, then you can look them up, but do this when you write them on in a different coloured pen so that you can see that they're things you need to work on remembering. Okay, moving on. So we've already looked at 3 indicators so far, but there are many different indicators. Some that only show you alkali, some that only show you acid, and some that show you acid, alkali and neutral. Universal indicator is the only one that gives you a different colour for each pH. So the one we are going to be looking at is called bromophenol blue, or also known as bromophenol blue. Same name, same indicator, just a different name. In an alkali, it's blue. At neutral, it's green. And in an acid, it's yellow. So it only really changes colour around pH 7, about 6.5 to about 7.4, you get the nice green, if you're going to be really exact. So it's good for neutralisation because it's very sensitive. One you would see often for neutralisation reactions is phenolphthalein if you're neutralising an alkali. So it's pink in alkali and loses all colour at neutral. Today we're going to focus on bromophenol blue, or bromophenol blue. So, bromophenol blue indicator. It's a very sensitive indicator, as I said. In an acid it's yellow, in neutral it is green, and in alkali it is blue. You can see that here. And this is how you buy it. And it is often used for neutralization reactions due to the dramatic colour change. So if you remember universal indicator, you get dark green at around 8. And sometimes that can be hard to distinguish between that and the green for 7. Whereas with bromophenol blue indicator, you don't have that issue. It's only green at neutral. So we're going to have today's fun fact zone. It's about these 2 gentlemen here. In 1923, Arrhenius's theory of neutralization was expanded on to form a theory of acids and alkalis. Now, hopefully you remember Arrhenius came up with a theory for neutralization. We went over this last lesson. Now, this expansion was done independently, but at the same time, by Johannes Nicolaas Bronsted, who was Danish, and Thomas Martin Lowry, British. Now, they didn't work together, but they both published their work separately with very similar ideas. So they're both credited with the discovery. Now, their theory collectively became known as the Bronsted-Lowry theory of acids and bases. Now, they did not win a Nobel Prize, but their theory is one of the most widely used for understanding acid-base, and as a result, acid-alkali reactions. Now, you will learn more about this theory during GCSE and A-level if you go on to study chemistry at A-level. This is just a bit of an introduction to them. Okay, so in your booklet you've got this page with your method. So what's going to happen is measure out 50 centimetre cubed of hydrochloric acid using a measuring cylinder. Add 2 to 3 drops of bromophenol blue indicator and swirl the mix. The solution should turn yellow. Then going to add a spatula full of bicarbonate of soda to the acid. This is the alkali. You're going to record your observations in a table what colour the solution went, and if that means it's an acid, alkali or neutral solution. You're going to keep adding a spatula until a colour change is seen. Now ideally you'd be taking it to neutral for neutralisation, but when we're adding spatulafuls we don't have that same control as when we can add things dropwise. So it's quite possible that we're going to overshoot neutral. Now, before I show you the video, I'm going to show you the results table. So you've got it like this. Now, it's actually going to take more spatulas than we have space for here. So I want you to put 0 at the top, the colour, any observation, and if it's acid, alkali or neutral, then 1, 2, and then the last 3 underneath. So you're going to skip the middle ones, because between the first spatula and the last one, not a lot changes. Okay, so now we're going to watch the video. So we've got our hydrochloric acid. This is our sodium bicarbonate. That's the chemical symbol for it. Going to accurately measure out 50 centimetre cubed of hydrochloric acid. Very important to wear goggles because it is corrosive. Place that in our conical flask so we can safely swirl when we're adding stuff, and add some Bromophenol blue indicator, which has gone yellow. And add a bit more because we want a nice strong colour so we can see changes easily. I'm going to add a spatula of bicarbonate soda, and it's going to mix. Tight sounds for like effervescence. That's fizzing. We're going to swirl it, and then once the fizzing has stopped, I'm going to check the colour. We're going to keep doing this until we get a colour change. So 1 and 2, this is number 2, this goes in your table. Good swirl, make sure it's all mixing, and the fizzing dies down. But we're still on yellow, so we need another spatula. Same again. So don't record this one, number 3 or number 4, because you've not got space in your table. And it's just the same thing happening. 5, don't record this one either. Now number 6, you can start recording this again in your table. So we're getting closer to neutral. 7, still getting fizzing, bit of swell, we're still on yellow. Our spatula 8, less fizzing now, good swirl, and it's gone blue. So we've gone past neutral. So make sure you've got 0, 1 and 2 in your table, and 6, 7 and 8. And the colour and any other observations, and if that means it's acid or alkali. Okay, pause the video if you need to while you fill these in. Okay, so I'm going to go through it now, and here are mine. So at 0, we had a yellow solution and it's acid. When 1 spatula was added, we had a yellow solution and fizzing, meaning it's still an acid. 2, 6 and 7, it's exactly the same. At 8, we've got a blue solution, and that means it's alkali. So we've gone past neutral. Now, as I said before, using spatula fulls, it's hard to control to get the exact point of neutral without overshooting. And that is why we've gone past to alkali. Now underneath you've got to fill in the blanks. There's a few errors in it, which I've highlighted here. So if you can, cross these out. We're going to write in the answers, the correct things around it. If you want to get a bit of paper and glue it over to make it a bit neater, you can. We will try and get you a handout when you do come back to the classroom as well. But if you can, cross it out to make sure the information is correct for your revision for now. So to start with, it should be hydrochloric acid, which is HCl, capital H, capital C, little l, and that is an acid. When indicator is added to it, it turns a yellow colour, which means it is an acid. In order to neutralise it, sodium bicarbonate has to be added, and you have to add 8 spatulas instead of drops of sodium bicarbonate instead of hydrochloric acid in order to form an alkaline solution. This last bit has been cut off a bit in your booklets, so make sure you have this correct. Pause the video, go back and forth if you need to see where I've crossed things out, just to make sure you have the correct information in there. Okay, moving on. So we're going to go through the reaction a bit. So we learnt last lesson that an acid and alkali react together to give water and salt, like so. And we learn about naming conventions with the salt as well. Now, this reaction is a bit different. Instead of a hydroxide as an alkali, we've got sodium bicarbonate, and we've still got hydrochloric acid. So following our naming conventions before, we're still going to get sodium chloride. So the metal, the top name in the alkali, chloric, hydrogen chloride. So we've got a chloride, so we've got sodium chloride. But we've got this carbonate here that we didn't have when we had the hydroxides. And that's what caused our fizzing. And that gives off carbon dioxide. Now you can do this reaction at home if you are very careful and ask an adult. And you can do it with vinegar and sodium bicarbonate, or vinegar and baking powder, or you could use lemon juice if you squeeze a lemon. Remember, ask an adult first to check it's okay to use these and to supervise you while you do it. If you haven't yet and still wanted to extract the indicator of the red cabbage, you could combine that with this neutralization reaction and you would see the change. But remember, be careful and ask an adult. Now, on your study zone, I have this link for you, neutralization and bath bombs. So if you follow that link, you'll get a video up. And this video is looking into how to make the fizziest bath bomb. And it's going through how to design an experiment, how to make sure it's a fair test, and how would you even measure fizziness. Now, some important things to know when you go to watch this video is the reaction. We're using sodium bicarbonate again. That is our alkali. But instead of hydrochloric acid, because that's quite nasty and corrosive, they're using citric acid. So what you're getting is, because we've got citric here, you don't need to know this, but it becomes sodium citrate. And like before, because we've got the bicarbonate, carbon dioxide gas is being given off. So it's still a neutralization reaction. And also, they're going to mix the two, the acid and the alkali, together as solids, but nothing's going to happen then. Now, if you remember back to year 7, when you learned about solids, liquids and gases, hopefully you remember solids, particles in a solid, can't move much, just gently vibrate. But as they go into a liquid, they have more energy and can move more. And when we dissolve, we're putting it in a liquid. So that is why water needs to be added, i.e. the bath bomb needs to be added to the bath with water before this reaction takes place. So these two have the necessary energy to react. So watch the video and look at how you can measure fizziness, how you can design your bath bomb, and all of this is taking place at a factory in Cardiff. Hopefully you've watched that video and you have got homework to do. Now in your booklet it says homework 4, but it's actually homework 5. And I'm going to show you how this works because I've put the word search online for you to do. So if you come to your study zone and you click homework 5, it will load up. It may take a minute to load just because it's quite, and you've got your word search. Now you are going to have to scroll down a bit and you can see your words. So if you come back up, say we're looking for acidity, you can have a look through. Now the grid's going to change every time it's loaded, so it's not going to be where it is on mine. So I found it, click on the A, drag down, and it will highlight acidity. One of the nice things about it, if I just pick a random thing, it won't stick. It will only stick if you've found the word. Once you're done, you can click check. Ignore the time spent. It's not actually measuring time, it's just a feature it has. And this is so that you can get the homework done before next lesson. And as always, there's a quick self-marking quiz under this lesson. So make sure you have a go to check your learning before you finish. And make sure you add any new words to the table at the front of your booklet. Now, if you are finished early, you can use this time to go over any homework you've not managed to do yet, or to check any other work. Thank you, Year 8, and I'll see you again for our next lesson.